Afternoon, everybody. Project 8. My project title is optimization driven machine learning framework for predicting laboratory algorithms in 30 environmental data, multiple case study. I'm Dr. Daniel, my colleague, Sister Nell Williams, Jaren, and our mentors are Dr. Iyiola and Amara. So our project is going to be focusing on predicting respiratory disease within both Baltimore City and Baltimore County. Respiratory disease remains a major public health concern, especially in urban communities where socioeconomic and environmental factors often increase exposure and affect health outcomes. Factors such as air quality, population density, traffic activity, as well as access to resources often allow some communities to face greater risk than others. So with our project, we are going to be using machine learning and artificial intelligence to identify patterns within these factors so that we can predict better where the respiratory health risk lies within the community. We chose Baltimore City Baltimore City and Baltimore County because it offers a diverse profile, diverse neighborhoods, different population characteristics, as well as different environments, all allow us to be the perfect environmental justice case study, which will allow us to see where the health disparity lies between both city and county, and if it's even equal at all. We're going to be comparing we're going to be using optimization to see if we can help better data-driven decision making. And yeah, so building on to that introduction, let's just talk about a research question. How can optimization help with the machine learning to be more predictive as well as more reliable in public health goals? So we're going to be using support vector machine, random forest, extreme learning machine, as well as a Douglas optimized support vector machine. So our project is going to contribute to us in 3 ways. First, we're going to have a direct comparison between all 4 of the models I just mentioned. And second, we are going to see if optimization can even help support the regular standard version of SVM. And third, we are also going to see whether this framework can be applied in different similar health risk studies as well as in other urban communities.
Hello, everyone. While we were looking through our literature, we found there's a narrow perception of respiratory health throughout the Baltimore community. We learned that they are using machine learning, but they're not adding optimization algorithms. They're not looking at environmental justice indicators, and they're definitely not combining other parts diseases. I personally feel like our literature was a little limited, right? But that's why our research here is extremely important.
This being research gap, we're going to look at the limitations of our final research. First of all, many previous studies when we look at one type of disease, if our research was looking at 4, those being respiratory cancers, diabetes, CHD, also asthma. Next, the geographic data sets were limited. This the next those previous studies from being able to be applied throughout different type of communities. Next, many different studies don't really apply what's with the machine learning models. That's one mission for different points, ELM, SPM, DFM, also worse. And then the combined effects of the population pollution, socioeconomic conditions, and other factors remain underscored because of our research gap. Our research gap, basically the pathways connecting those 4 different respiratory health risks that I mentioned earlier, really underscored due to previous research limited. And that leads us how we're going to address that gap by utilizing those 4 different machine learning models to essentially compare the different results that we get from those different factors.
So now we're going to talk and the research work. We're going to talk on to the methodology we link on to copies from. Well, first of all, we posted data and to mention earlier in the research here. We have researchers who are focused also on the air quality and the ozone loss in the airway, found in the ozone, all the gases that bring about these respiratory health risks without having to consider what is possible between, right? So if I look at the data from the BPI, those videos do always talking about if combined on everything that goes on. There's a childhood age, unemployed people, all the factors that we're looking at. So it was wrong. So we have to put this up. That was the next step after going to the data. We have to put these reports of there's the family, the student, we usually voluntarily. So we're trying to have a So we have to do lots of celebrating to make sure that we are feeding our movement, we are spending money to actually be able to do the about that really. So, and then we encourage them to do analysis and different directions, so we're just trying to see what our data we but it kind of gives us what steps we need to take. Let's say if our data is key from the graphs that we're looking at, or if the data is announced, what steps should features of mentioned, we have a lot of tracks, a lot of variables to look at, which we're gonna see in the next slide. So we have to select the features that are driving our target environment, right? And we're working to the model, optimize the amount. This is key for our project because we're trying to optimize the model to see how well it can get restoration time. So the thing is, it's like I'll talk about the data and the model of the group. Which I already shared the model, so we use the data, so I put them together. And then because we have over 80,000 census tracts that we have to narrow down to just Baltimore City, Baltimore County, with that for Tennessee, right? The issue that is like, for example, especially from quality of the students, we are also making already we're looking at the population, the health indicators, the social economic factors, right? And that's already mentioned by Jerry, the money that we income is as the Iyiola and market first and would be much more beneficial. Now we can move on to the next slide where I'll talk about the question evaluation. So which shows how we use cycles, cycle when we use the component in the unemployment chapter 12. So initially what we gave the changes we said in the 80 and 20. So 80% for training and 20% for testing, right? But we also go on the step early depending this mean stems from our exposure data analysis, right? So we had lost that areas to do consolidation. We found that process see and train the data in different tools. So we the powerful and the simple. So if we see the stratified table, I would see that one. So we the stratified table consolidation. So what they can do is just the number for they can be K can be by K can be just like X in nothing. X times three, not X can be right, so we're staying in five. So what we're trying to do is, I'll do an example of five. Let's say I have five. So I took my data on the first four, cherry on the three, four. Get my data on the one, two, three, and we say one, two, three, five. There's it on the for element beyond the stuff, okay? So that's what we're trying to do, and then we get the average. That's kind of so training the model in a way that it's able to read different types of data, different vector just against basically have multiple data. Um, all the balancing the shop, the balancing strategies to balance our data so that we can avoid bias. We'll move on into the demo video that we just showed the process from start to
The RDSI contains features that I talked about, environmental and socioeconomic. These are the variables that are listed in our code. We talked about those a bit. It's things like particulate matter, poverty, ozone layer.
Together, these variables help identify patterns associated with elevated cancer risk. Before training the models, the data is cleaned by adjusting missing values and selecting most important groups. The data is then divided into training and testing sets. To improve model reliability and reduce the effects of classing down, boundaries such as cost values are applied to full model training. After training, each model is evaluated using most performance metrics, including accuracy, precision, recall, F1 scores, AUC, and prediction error. These visual comparison plots evaluate each model's predicted performance and determine which approach provides the most reliable application of environments associated.
Okay, so this weekend our results and key findings. These are results and key findings for we find product validation. So our first main one was the SDM and this optimized SDM that the highest recall score. Recall score essentially measures the amount of relevant digits and how you able to detect them. Next, we have reinforced delivered the strongest predictive performance that the highest accuracy, precision, F1 score, and RCDC score. However, the model did have 200% in the percent versus RMSD, meaning that the model is really unstable and maybe suffering from overfitting due to that high number of percent difference. And then third, we had ELM, if we look at the same graph on the right, the percent versus RMSD. The BLM model had the lowest percent difference, essentially meaning that it had the most stability before we talk about valuations. And if you look at the bottom, we have a table of all our metrics and all four of the consumer models. Essentially, this is the metric that we use to essentially measure how effective the model is performing. The next one, these are results after cross validation. So mainly after cross validation, if you look at that same percent of the RMSD graph, all of the percents on all the models went down with the exception of random tours still being at 200%. This essentially means that the data also may still be suffering after cross validation is still suffering from poor filling. This means that although random tours still have the highest accuracy, they didn't necessarily perform the best out of all our models. The model that did perform the best was the Douglas optimized support vector machine. And it was also the most stable, as you can see, it did have the lowest percentage of but essentially our overall findings from this data after cross validation is that all of our models essentially became better except for the random scores. And then our Douglas optimized was our best program model as well.
So thank you, Chris. So now that we've gone over both before and after cross validation results, let's interpret this. So as you can see, random forest had the highest accuracy between all the models. However, it also had the largest RMSE difference between both before and after cross validation, meaning that between testing and training data, it's being overfitted. Now, ELM had the second highest repo. However, it also had the largest ROC, sorry, it had the lowest ROC AUC, meaning that, as well as an RMSE percentage difference that was smaller than SVM, meaning that overall, trying to classify, it's not the best at classifying, given that the thresholds where to start changing. However, SVM and Douglas SVM, while it initially did not have the highest accuracy, we understand that, it had the smallest RMSE difference, meaning that it's able to generalize the data well as being able to remain stable despite the thresholds changing. So how does this connect to our research question? Well, it connects directly. We set up, the second thing I mentioned was that we want to make sure, can optimization make the standard SVM better or worse? And our hypothesis was proven partially. Given the statistics, it was that accuracy and precision did not increase. However, ROC, AUC, F1 score, repo, in generalization stability, as well as the RMSE percentage went down significantly after we did our Douglas optimization. So we did prove our point. The biggest insights and the biggest takeaways are that accuracy does not always mean reliability, nor does it mean stability. RF had the highest accuracy, as I've already mentioned. But just because it's accurate does not mean it's good for public health use. In public health, it's normally generalized. It's okay to have a lower accurate model if it means it's more stable and able to generalize to new data. That's important because these false negatives and these false positives can lead to a lot of issues. For example, we think about funding. If you were to divert funding based off of these statistic models and use random forest, it would have a lot of false positives and false negatives. That could lead to allocation of resources being put in the wrong direction. And the communities that actually do need it will end up not getting. So it's really important that we touched on that. And some of our unexpected findings that both before and after random forest cross validation, it still had the largest RMSE difference. It was very, very significant. It was 200%, as you saw in the graphs. And that ELM did have the smaller one had the smallest RMSE difference before cross validation, but after it had one of the highest. And of course, our DSVM, our optimized model, had one of the larger RMSE differences, but then after we did our cross validation, it ended up actually going down to one of the smallest, which I think that's a really important question.
The first moment was trying to figure out which feature exactly we're going to need, and which feature pushing our with features from audio on the environment. We have to optimize our model in a way that is not overfitting by Phoenix giving us the metrics that we need Of course, it took more time to processing the data, trying to prepare the data, trying to make sure that it's really not, and it's also like overfilling for our information and for student that. So, yeah, so again, the strategy example is what we lean on more so that we can get different variances of our data so that our models can also learn different targets instead of just looking at one variant, gravitating towards that variant and then we test and it doesn't perform well on how we look at. So I'm also document as we saw from the results and the metrics, the point validation does enhance our metrics of the metrics. And also the various optimize algorithm did improve our this data from the metrics that the results that it showed reducing need to choose less than 5% percentage change. So we'll move on to the next slide that talks about the limitations and responsibility.
So for our limitations in our project, one of our first limitations is that we only use 4 different types of machine models. If we were to use different types of models, we always for different types of outcomes after we train those models. That's that leads into the research being limited to 40 certain areas, and our research being in certain in urban areas. If we were to try to use these same models and maybe a more rural or suburban area, we may not have gotten the same goal as we did using the models in urban areas. And then this also applies the finest framework to cities with significantly different and types of environmental conditions, but different weather, different climate. This can also make a difference with these same models. You know, with responsible AI, as we mentioned earlier, accuracy isn't the only measure that um, basically determines how good a model is. We have to look at all the metrics and compare all the inputs to essentially determine which model is the best. And then next, we have models with performance should be evaluated across different types of demographics. This is because we need to prevent bias in our models to be consistent throughout all the types of demographics. And then next, model vision should not replace humans or public health professionals, but rather assist them in making good decisions. And then finally, privacy, transparency, and consumer modeling needed before these models are fully consumable.
And to conclude, social, economic, environmental factors can help predict what the results we both know. We found that random scoring didn't change the accuracy, but that was SPM that would keep instability and stronger generalization, which we would prefer because we would prefer consistency. In the future, we will improve double. We will explore more fairness and fine tune ranking boards so that we can create a reliable and responsible public prediction. These are our reference themes, and we would like to acknowledge Amara, our graduate mentor, and our faculty mentor, Dr. Iyiola, for this process and putting up with us through this. And we're open for questions.
Great, can I ask a question from the audience?
Yeah, I question why wasn't deep learning say I know you for how much probably deep learning where they consider the project.
Yes, so we did consider it initially when we were first exploring our research opportunity in question, the Black and respiratory disease. We looked into the previous research already done with deep learning, and we had saw that machine learning was more effective. We tried different types of machine learning, we just did regression, but with our problem, given the features that we're using and how we're trying to vary the features and see how the patterns align within those, we figured the statistical regression was not a good one at all as well. But with the deep learning, like I just talked about, we the research was kind of already done that it wasn't very effective, so we didn't really try to like go down a route that's already been done, like something that's saw and done. So we just kind of focused on the machine learning aspect and optimizing what's already out there and seeing how we can improve it.
Okay, so the Brooklyn how doing that? We have multiple meetings in the day. So you were trying to like be important. However, there is a high. Okay, so when we already down, we like the smaller meeting six to different ones last week from July, we got as well. We had it, that was so that we can lunch, and then lunch we not for different, and we also had tomorrow again. Or we were supposed to want the different. I guess that answers the question, why we did not you Yes. Yes. If you guys have more time, what would you approve?
So much that we want to improve on. I think that if we had more time, we want to improve on the target variables that we had used. Initially, we set up to use four, but due to the time restraints, we were only able to present one, the cancer research. But if we had more time, I'd honestly say that we want to improve definitely asthma in our research paper. We're going to be past this symposium. We're going to be looking into that with the asthma, seeing how CHD, coronary heart disease, affects it as well, along with diabetes. We wanted to look into that. Those were our four that we initially set out to do during the summer. However, due to the time restraints and the summer program being so short, we had to end up just taking the environmentally related cancer list.
And beyond that, because everybody but we are into coding and computing, right? I'm on the community ethics side. So for me, I would want more data from John Hopkins, University of Maryland, MedStar, GPMC. I want more information from even like the smaller, like a patient first and the urgent care. Because people, both more areas. I don't know if anybody else been doing both more areas, but we always go for urgent care before we go to a straight hospital. So I feel like sometimes those factors are definitely we're kind of left out because of our time as well as the timing.
I want to ask that I feel like you use by cross validation, you by to and check for cross validation. And why you didn't choose another type of cross validation?
Okay, so you're trying to say, well, we can go beyond the 5 to 10 for maybe try 15 for it or 10 for it.
Another type of method of cross validation.
Because we have different methods that we are looking at. So we look at care validation and we also look at balancing validation, right? So we, again, it's narrowed down to the time because we had, I don't know if you saw on the slide, we have various methods of balancing the data, which included more calculating as well as processing data. And we also have to have enough time to optimize, our model with the diagnostic algorithm. So as we also see, we only optimize the SP. If we have more time, we'll look into other metrics, other ways of. Okay, machine learning is a lot. There's just a lot that you can do, and you have a lot of options. Even with the balancing data, even with the algorithm, there's a lot of data. Adams algorithm, there's just so much you can do. So you have to at least have something that you are really more sort of word named without limited time. So yeah, that's only part of it. And then you have two things.
One more question. Were there any benefits seen between using platform cross validation and template?
Okay. So for the pipeline in the template, the benefit that we saw first from our think the three parts of the last slide, we did say that virtualization did improve our metrics and our results, our evaluation metrics and results, right? So from what we tested and learned is that different methods for different models performed differently on different codes. So we could see that the SVM performed really well on the 5 code, but did not perform too well on the 10 code. And we could see that the ALM performed very well on the 10 code and 10. So different codes give us the ability to see how different models do pair with different codes. Did that get it? Yes. Okay.